Okay, so normally the next step we would do is evaluate our priors. And again, we're not going to do this with this model at this stage. We're going to evaluate them later. But we will evaluate them at this stage for all of our other models. And then our fourth step is to run the model. So to run the model, you use this stand command, and then you enter all the different parameters that you want to specify for running this, and then we assign the results to a variable name, just like with any other thing in R. So I'm going to assign all of this to an output called standFit. So the result of our Markov chain Monte Carlo sampling is going to be written to this file. And again, you can call this whatever you want. And so we can step through this. So we need to specify what file contains our model code. And so before we called it model.stan, and so this needs to have the same model. So you can change the name of that model, but then you need to remember to change it here too, because this is where you're telling Stan where to find the code for the model. We also need to tell Stan where the data are. So remember the data list that we created, that was the first thing that we did. We have to tell Stan where our data is. So we're saying our data is in this file called data list, or our variable called data list. We also have to tell Stan what parameters we want to save for the results. So in this case, we just have one parameter that we're estimating, and we want it to show us those results. So we're specifying theta. And remember, we called it theta in our model, and so we need to call it theta here. If you call it something else in the model, you need to call it something else here. We need to specify how many steps to allow for the warm-up. So it's similar to the burn-in, where we don't know ahead of time how long to make this, but Stan actually it's very quick at kind of getting all the settings correct. So 2,000 steps is plenty, and we'll visualize this. We'll evaluate whether or not this is enough later. But this 2,000 is a good kind of default to use. Then we need to specify how many iterations, so how many steps it should take, so how long to run the model. And we're going to do 10,000 steps. And again, that's kind of a nice default. We'll evaluate whether or not this is long enough later, but it's a good place to start. And then lastly, we need to tell it how many chains we want it to run. So I always use 3 as a default, and then sometimes if I can tell the model's not exploring space well, then we can up this. I'd never use fewer than 3, just because it's nice to see. Well, you'll see why. Having 3 allows us to really evaluate if our model is exploring parameter space well. Okay, so if you run all of this, you'll see your computer is not going to do anything for a while. And that's because what it's actually doing is compiling the code. So you've written the model in C++, and your computer needs to compile that code. And so while it's doing that, you're not going to get any response to your screen. And that takes a while. But then once it actually starts running, it's going to run extremely fast, and it'll write things to your screen. So you just have to be patient. And everyone's computer is different in terms of how fast this process is. So just be patient. Okay, so at the end of that, so our model's done running. So before we actually interpret our results, what we need to do is to see if our Markov chain performed well, right? If it didn't perform well, then we don't want to base our interpretation of the data off it. So before we even really look at our estimates or at the data that's coming out of our model, we want to see if the model performed well. And there's a number of different things that we can use as diagnostics to tell if our model performed well. So a few things we might think about. So was our warm-up long enough? So did the chains center around a value prior to the warm-up ending? So this is analogous to our burn-in, like with our burn-in practice, where we want to make sure that our chain found a peak value before or kind of after the warm-up stopped, right? And that, or preferably still during the warm-up phase, so that our estimates aren't biased by the steps it was taking during the warm-up process. Another question we want to ask is, were the chains long enough? So did the chains center around a single value long before before they ended? And third, we want to make sure, did all chains find the same peak? So did our 3 chains center on the same value? So how can we assess this? There's a few different ways. So first, we can view our results. So if we do the command print and then our variable name that we called our model, so print stanfit, it'll give us this summary information, and we'll kind of come and go from this site here. So some information it tells you is the total post warm-up draws, so the total number of chains times the post warm-up length of the chains. So this is 24,000. So remember, we had our total steps was 10,000, but 2,000 of those were warm-up. So each chain had 8,000 steps, and then 3 chains. So 8 times 3 is 24,000. Then we have our different parameters that were estimated. So here we have theta, and here's just a bunch of information about it. So the mean, the standard error of the mean, the standard deviation, the highest density interval points, so 2.5%, 25%, 50%, 75%, 97.5%. We also get this for what's called the log posterior. So remember that Stan bases its calculations based on the negative log posterior. And so this, we're often just going to ignore this, but some things that we do are going to use this, but we'll ignore that for now. But all of your models are going to have values here for the log posterior. So again, we mentioned here that these can be used for calculating the highest density intervals, and the highest density intervals again can be interpreted the same way that most people interpret confidence intervals, but which is incorrect for confidence intervals. So in these results, so we shouldn't be looking at these values yet because we don't know if our model ran correctly. Instead, what we want to look at are diagnostics. So one diagnostic we want to look at here is what's called the R-hat, and we can see that it's 1 for both of our parameters. So what is R-hat? And they've actually changed how they calculated it in the past. So this explanation is a bit out of date, but the idea is still the same. So the idea is that each chain is split in half. So if these represent our 3 chains that we're exploring parameter space, each chain is cut in half. And then what it does is it calculates the ratio of the variance between each chain divided by the variance within each chain. And so the idea here is that if all 3 of our chains have found the same peak, then the amount of variance between chains should be the same as the amount of variance within chains. And that would result in this ratio being 1. Okay, hopefully that makes sense. Whereas if our chains are on different peaks, or if our chains have explored different space, then there should be more variance when we compare values between chains than within chains. And this is going to result in these R-hat values being greater than 1, right? If there's more between chain variance than within chain variance. And so there's no hard and fast rules as to how low R-hat needs to be to trust your model. So they should all be 1, then you know you're good. But really, as long as they're less than 1.1, then you're probably okay. If your R-hat values are greater than 1.1, then your model's probably having trouble exploring parameter space. So our R-hat values are 1, so that looks good. Another value that's given here it's called n_f. This is the effective chain length. And so Markov chain Monte Carlo processes always have some autocorrelation, which by that we mean just non-independence between steps. And that makes sense because they're Markov chains. So by definition, what happens in one step is determined by what happened in the previous step. And so what this is really an estimate of, it's the number of independent steps given the autocorrelation. So even though it took 24,000 steps, that's the same as it taking about 8,000 independent steps because there's autocorrelation. And again, this is fine, right? As there's always going to be autocorrelation, but as long as this value is over about 1,000 steps, then you should have good estimates of your posterior. Just a note on this is, by default, these are the intervals that Stan will give you, but you can customize that, right? If we're trying to get away from our 95% confidence intervals or intervals, you can just change this. You can set the probabilities to whatever you want. So here I've just changed them to 5.5%, 50%, and 94.5%. So these would be the boundaries of an 89% confidence interval, or sorry, highest density interval. So you can customize that however you want. Another thing that we can do to evaluate if our Markov chains ran well is to look at something that's called a trace plot. So what a trace plot is it's a visualization, so it's a plot of each step in the chain and what value the model was at that step of the chain. So if the chain is mixing well, so if it's exploring space well, then this should look like it's been called a spiky caterpillar, right? But it's clear that there's this noise around a constant value, right? So this means that our chain has quickly moved to a peak, and now it's just randomly bouncing around that peak, which is what we want it to do, right? It's taking some steps down, but it's always coming back to the peak. So it's clearly bouncing around the same mean value. This means that our chains are mixing well. They're exploring space well. Whereas bad mixing, like this is indicative of our chains moving to different peaks, right? So this chain was clearly on a peak where the mean was around 2, and then it found another peak where the mean was about 0.5, then it jumped to another peak where it was at 1, and so on. So clearly our chain hasn't finished exploring parameter space yet because it's still bouncing around different peaks. But what we want is to look like this. Our model should find a peak very quickly and stay on that peak. And so we can view our trace plots with this command stan_trace, and then the arguments that go into this command are the variable that we called our model. Then we can tell it what parameters we want to plot the trace plots for. So here our parameter was called theta. And then we can specify if we want to include the steps that were part of the warm-up. And so we're setting that to true. So we do want to do that. So here this gray area is the warm-up steps. And then the rest of it are the values that our model was at for the other steps. So you can see it only took our model like 2 steps to really get to that peak, and it did that well within the warm-up phase. So it didn't start actually collecting data until here. And so it's clear the warm-up stage was clearly long enough for our model to find the peak and really stay there. And so from then on, you can see our model is not bouncing around to different values. It's clearly found a mean value and has stayed there. And all 3 of our chains have found the same peak, right? All 3 of our chains are at the same value. Oh, so here I walked through that. So this looks good. This is exactly what I want our trace plots to look like. Okay, so now I've answered all these questions. So was the warm-up long enough? Yeah, our trace plot told us this because it found the mean long before we started recording data. Were the chains long enough? Yep, they all found that single peak even before the warm-up ended, so they were fine. Did all chains find the same peak? Yep, our R-hat value tells us that, and our trace plots tells us this. So it looks like our Markov chain Monte Carlo process went really well, right? Everything, all of our diagnostics look good. And again, you want to do this for every model that you run. All right, let's stop there before we move on.